But one thing I want to do in the lecture today is a few more quick applications of Cayley numbers in G2 that I forgot on Monday. Kind of fun. So I only need very few things. So when X was a Cayley number, we had two of the properties where it's norm-preserving. Another property was that x bar y is equal to norm x squared y. These are the only two I need today. So one consequence we already discussed last time, if I have a Cayley number of length 1, then both left translations and right translations are in SO8, regarded as SO of the Cayley numbers. So we discussed that. Then another fact is that if x is an imaginary Cayley number, this implies that if I look at the left translation and I square it, this is minus norm x squared times identity. I claim this is a consequence of this equation right here, because in this case x bar is minus x. So if I replace it with minus x, this is left translation, compose the left translation, and that's then minus norm x squared times y, so minus x squared times identity. Particularly if norm x is equal to 1 in addition, then Lx and Rx are complex structures. On R8, regarded as a Cayley numbers. In fact, so maybe one first application would be I got a 15-dimensional Lie algebra of Heisenberg type. By doing the following. So remember, when we discussed Heisenberg type, we had a map, I forget what we call it, phi, from the center into a vector space V, and such that phi squared was of x was minus norm x squared identity. This condition meant of Heisenberg type, and the Lie bracket was given by two Lie brackets in V. Inner product with an m to the center is given by phi of z VW. Right, so this was what we meant by Heisenberg type, and in our case, I can get such a linear map from imaginary Cayley numbers into the Cayley numbers. So this is 7-dimensional. This is 8-dimensional. That's my center here, just by sending x into left translation by x. Right, then this identity here precisely means this of Heisenberg type. Right, so Cayley numbers give rise to a 15-dimensional Lie algebra Heisenberg type, which is important. Okay. Another application is that tangent bundle of S7 is trivial. By doing the following, take an x which is an imaginary Cayley number, then I can define a vector field. Let's call it y sub x on S7. Sphere of radius 1, by saying y sub x, or the foot point p is x times p, so left translation of x applied to p. That's orthogonal to p because for an imaginary Cayley number, Lx is Q-symmetric. Did I mention that? I didn't mention this, right? Another property we've proved that this is minus Lx if x was imaginary. So it's Q-symmetric. So that means that this gives me a vector in the tangent bundle. of S7. And of course, Lx of P is non-zero for all P. So it gives me a non-vanishing vector field on the tangential bundle of the sphere. If I take an orthonormal basis, x1 up to x7, or the imaginary Cayley numbers, I get vector fields y x1 up to y x7 on S7, which are linear independent. At all points. Right, because if I take a linear combination of ai, y, xi, that's y summation ai, xi from the way it's defined. And of course this is non-zero for every point P. So that's again the imaginary Cayley number. And remember, I think I mentioned to you proposition. Tangent bundle of Sn is trivial if and only if n is equal to 1, 3, and 7. 1 and 3 is if you want to, just because S1, S3 is illegal, but S7 is not illegal, but nevertheless left multiplication of Cayley number is good enough to define linear dependent vector fields. So that's say a second application. The third one is following facts about G2. So remember, G2 was the automorphism group of the Cayley numbers, and they are determined by the fact that I goes to E1, J goes to E2, epsilon goes to E3, where epsilon I is an orthonormal basis is orthonormal vectors in the imaginary Cayley numbers such that E3 is orthogonal to E1 times E2. And conversely, so if I have such an orthonormal basis, then this gives me an automorphism. Right? So that's our characterization of the Cayley numbers. This now has the following implications, which are kind of interesting. First is a fact about S6. Remember, S6 as a homogeneous space is SO7, not SO6. It's a standard way of viewing a sphere as a quotient of corresponding orthogonal groups. SO7, of course, acting on R7, which acts on the 6th sphere. And now we get another equality that this is G2, not SU3, where remember that G2 sits inside SO7. Of course, another fact for the Cayley numbers was that out of the Cayley numbers is a subgroup SO7. So first we proved it's non-preserving because it takes 1 to 1. So I can regard this as SO of the imaginary Cayley numbers. And therefore it's a subgroup SO7, so it acts on R7. So here G2 acts on R7, therefore it acts on the sphere, and it acts transitively. So that's one equation. Another equation is that if I look at the unit tangent bundle of S6, this is G2 not SU2. I can also regard this as what I call the two frames in R7. So two orthogonal unit vectors. Right, what is this here? It's a unit vector in R7, and the unit vector in the tangent space is orthogonal to the foot point, so it's two orthogonal unit vectors in R7. It's another way of regarding the unit tangential bundle. It's called a Stiefel manifold. I also have the Grassmannian of two planes in R7, and this becomes G2 mod U2. So now we and one more property is that SO4 is in a natural way a subgroup of G2. And of course here in part B we have to see that SU3 is a natural way and also a subgroup of G2. That's essentially all the subgroups of G2, which I can mention at the very end. So let's prove some of these. Let's do part A. So that's maybe the most interesting one. So G2 acts on R7, imaginary Cayley numbers. And from this description that it's uniquely determined where it takes E1, E2, and E3, and they're arbitrary with only this additional condition, it says I can send E1 anywhere. So I think this implies that it acts transitively on unit vectors. Well, maybe I should say I have two unit vectors, right? I can take one automorphism that takes I to the first unit vector. I take another one that takes I to the second unit vector. And one times the inverse of the other then takes one unit vector to another unit vector. Even more than that, if I take two orthogonal unit vectors, any two orthogonal unit vectors, I can take them into any other two orthogonal unit vectors. The three I have to worry about, but the first two I don't. So it says also that it also acts transitively on two frames, what we call two frames, and hence on unit tangent on S6 also. Right. Now I want to show that the isotropy is SU3. So G2 acts transitively. That means that S6 is G2 mod H, where H is the isotropy at some point. So an element in G2 such that, for example, G of I is equal to I. Right, G2 acts at the imaginary Cayley numbers. So pick out a unit vector, say I for simplicity, and that's the isotropy at the point I, which means I can then get an identification of S6 with G2 mod that isotropic in the usual way. Right? So let me now describe what is H. So I want to claim that H is, as claimed over here, SU3. So let's see what this here means. Remember, G was an automorphism of Cayley numbers. This holds for all A and B. So let's set I equal to A equal to I. But G of I is I. So this must be satisfied. So what does that say? It means that multiplication by I commutes with G. So let me say it as follows, that G composed with Li is equal to Li composed with G. Right, that's what it says. So it means it's, I claim, complex linear. So remember, Li squared is minus identity. It's a complex structure. And G lies in H implies G is complex linear. And another property it has is that it certainly takes I 1 to 1, that's an automorphism, takes I to I, because it fixes I, and therefore preserves the orthogonal complement. That's an isometry. And leaves the space invariant. And Li also preserves the space. So I get a complex structure on this vector space. G acts on it and commutes with the complex structure. So that means that G is an element of the unitary group of that complex vector space. But orthogonal complement inside, this is 6-dimensional, complex 3-dimensional, so it's U3. Okay, so just from the definition, I immediately get, and the automorphism property, I immediately get it must be complex linear. We're almost there, but not quite. Right? It's not U3, I claim it's SU3. So let's see how we can do that. First, recall some things we proved last time. Dimension of G2 is 14, and pi 1 of G2, pi 2 of G2 was 0, and pi 3 of G2 was equal to Z. So that's what we saw last time. So what does that mean about H? What's the dimension of H? Right, I know that G2 not H is a 6 sphere, so it must be 14 minus 6. It must be 8-dimensional. Of course, the dimension of U3 is 9-dimensional. So it can't be all of U3. Dimension of SU3, of course, is 8-dimensional. And SU3 sits inside U3. So now our claim is that must be the subgroup inside U3, which is H. So here sits H. I want to claim if I can show that it lies in here, then it must be equal to each other by dimension reason. H is also connected. So, in fact, what can I tell from the long homotopy sequence here? We have a vibration from H to G2 to S6, because S6 is G2 mod H. That means that I also get that pi 1 of H, first pi 0 of H equals pi 1 of H equals 0. I guess even pi 3, although it doesn't matter. But so H must be connected, right? So if I can show it lies in SU3, I have a connected subgroup with the same dimension SU3, it must be SU3. So how can I do that? I can do it as follows. I can take a homomorphism from U3 to the unit circle, which takes the matrix to det A. Det A lies in the circle inside C. That's a homomorphism. And the kernel of pi is, of course, SU3 by definition. So I'm going to show that H lies in the kernel of pi.
It follows from the composition of blocks. Those subspaces.
Pardon?
You have invariants of subspaces. So you can decompose it in the block form. In the first 2 by 2.
This is C3, right?
Yes, but I will see it as R6.
Sure.
And I also have the generated by the unit and I, and that is fixed. So in the block 1I, it's identity, and I have the remaining block, but as a whole, it had determinant 1 because it lied in SO7.
So as a real matrix, it has determinant 1. Does that mean as a complex matrix, it has determinant 1? Probably not, because I think at some point we show that U3 is SO6 intersected with the linear, complex linear maps. So that means that this 3 by 3 complex matrix as a real matrix has determinant 1, even if this one doesn't. It's a different matrix. Right, so it's not quite obvious. But of course, what can happen? H is connected, so H sits inside here, right? H is connected. I can restrict the homomorphism to H, so the image is either trivial or the whole circle. If it's trivial, I'm done. So I have to contradict the assumption it's onto. To find a contradiction to the assumption it's onto. So if pi from H to S1 is onto, then I claim S1 is H mod H prime, where H prime is just the kernel of pi restricted to H. So this is onto, right, that's clear. But H and H prime are compact. Well, I'd say H prime is compact. But it's a kernel, sits inside U3. U3 is compact. So it's a compact group, and hence has finitely many components. So that means, let me finish it here. Now I'll use the fact that H mod H prime is a circle. It means I have a fibration H prime to H to S1. I have a long homotopy sequence which says that pi 2 of S1 to where do I have to start? To pi 1 of H prime to pi 1 of H. Probably don't need that. To pi 1 of S1 to pi 0 of H prime to pi 0 of H to 1. This is an exact sequence. What do we know? Let's look at the tail end. This here is Z. This is 0, as we argued over there. Right. H is connected, so this is also 0. So here I have a 0, here I have a 0, which means this must be an isomorphism. So that means that pi 0 of H is Z, of H prime is Z, which means I have infinitely many components. That can't be H prime is compact. I don't know if there's a simple proof in that, if you can think about it, but that's one way of showing it.
For example, if you use the definition of G2, it's an homomorphism. A of xy equals ax times
Yes.
ay.
Yes?
If you take, for example, an eigenvector x,
Yes?
you take a of x squared.
So AX is lambda x. Take A again. Is that what you want to do? No?
A
Sorry.
of x squared.
Ah, okay.
Equals a of x squared.
All right. Because lambda squared, x squared. And so lambda is complex. X is a Cayley number. I have to use a fact now that, say, 2 elements span associative algebra. So I can factor it out like this. Which now means what?
It's x squared.
X squared, oh sorry, yes. Which means
I'm trying to prove that must have determinant 1.
yes, I understand. But I have to look at the eigenvectors of the complex 3 by 3 matrix A, not of the real 6 by 6 matrix A. Right, this was his problem also, right? So the 6 by 6 has determinant 1, I know that. I have to show the complex one has determinant 1. Here I'm looking at eigenvectors of the real matrix, of the 6 by 6, or the 7 by 7 matrix, right? I know it has determinant 1, it lies in SO7, right? So that probably does not do it. But anyway, so that finishes A, right? So we know this here. This is just as easy now, I claim. It just follows from what we did so far, because unit tangent bundle of S6 is now G2. Right? It's transitively on 2 frames. And what's a stabilizer? Is a stabilizer, say, of I comma j. Right? So I can regard this as elements A in SU3, which was a stabilizer of I, such that A of j is equal to j. That implies that A lies in SU2. But the matrix in SU3, it fixed the vector, is just SU2. And it has the right dimension. And this here has dimension 6 plus 5 is 11. That means that the stabilizer must have dimension 3. The G has dimension 14. So that must be the stabilizer. Let me not do this one here, but let me indicate E, which is interesting. That's a very useful subgroup of G2 if you have to study G2 in more detail. So I claim SO4 is a subgroup of G2, so I have to construct automorphisms of Cayley numbers for each element in SO4. So let's do the following. Let's define a map from SP1 cross SP1 into G2, which goes as follows. Take 2 unit quaternions and send it into the automorphism, which takes A plus B epsilon, that's a Cayley number, into Q1A, Q1 bar, plus Q1B, Q2 bar, times epsilon. So now I have to verify the following things, which you can leave as exercises. A is an automorphism. So I have to verify the automorphism property. I can crank that out. It's not too hard. Isomorphism. It's another thing I have to crank out, which is not hard. And the last one is the kernel of pi is plus or minus 1, 1. I claim this inclusion is clear, right? If Q1 and Q2 are both minus 1, then this is trivial, and this is also trivial. So claim is that's the whole kernel. Right? That means I get an induced map from SP1 cross SP1 divided by the kernel, embedding into G2 homomorphism. And of course, this here we saw was SO4. So I have an embedding of SO4 into G2. Right. So it's another interesting subcode of G2. And what one can show is the following diagram, which is not quite obvious, not so easy. At least that's what we know right now. This is a diagram of all subgroups of G2. So we saw there's an SU3. Now over there we saw there's an SO4. In SU3 I have a U2 that also sits inside SO4. In U2 I have an SU2 which contains a circle, because I also have a T2 inside U2, therefore inside SO4. That's a torus inside G2. Inside the torus I have a circle of any slope P comma Q. Interesting one is that I have another one in SO4 which I want to call U prime 2. I'll see in a minute what that one looks like. It also contains the torus T2, contains another SU2, which also contains a circle. So these are inclusions that all follow from the fact that I constructed these two subgroups of G2. There's one more, which is an SO3, which is the maximum subgroup inside G2. There's nothing in between. I forgot one more. There's a subgroup inside SU3, which also lies inside SO4, which is SO3. But there's an SO3 and SU3 that we discussed before, which contains a circle. And I think that these three circles are all different circles. Namely one of these circles here, forget which one. So it's a complete picture of all the possible subgroups inside G2 with all the possible inclusions among them. Now let me just say a few words about this U2 and then I'm finished. So I claim inside SO4 I have two U2s, which sounds kind of funny. And U prime, so U2 is the usual one. Right here we identified C2 with R4 in a certain fashion, and that defined an embedding of U2 into SO4. We sense A into V goes to AV. So now I define a U prime 2, which is the following one. Take an element in U prime 2 and let it act on C2 as V goes to A prime V. So conjugate the matrix and let it multiply the vector. Okay. And now identify C2 with R4. And then this linear map defines a linear map in SO4. So this U prime 2 now lies in SO4. So in principle, there are two different embeddings of U2 in SO4. And now here's the following exercise. U2, U prime 2 are conjugate in O4, but not in SO4. So in that sense, there are really two different subgroups in SO4, although in O4 they're the same. So as a hint here, take the map from the quaternions to the quaternions, which takes Q to be Q bar. So interpret that element as an element in O4, and the claim is that element conjugates this one to this one. So that's the exercise. Then the other exercises, there's nothing like this in SO4. And you may recognize this map here from R4 to R4 as what in one of the exercises is claimed to be an outer automorphism of SO4, but not inner. Right, so that's connected to that exercise. Nevertheless, you'd say, well, it's more or less the same thing in SO4 anyway, right? So how can it be that much different if I now take this inclusion and go into G2? So I claim, so the next exercise, which is not so easy, U2 and U prime 2 are not conjugate in G2 and not even for some automorphism A in out G2. And the reason is since out G2 is in G2. So every automorphism of G2 is inner. Unlike for SO4, there's an outer automorphism. For G2, there's not. And these two groups even can be distinguished topologically in the following way. That's kind of a fun fact. So connection is topology. So I want to show that these two SU2s inside U2 are completely different subgroups. And I do this as follows. Like, let's look at the map from SU2 into G2, and look at the induced map in pi 1. In pi 3, sorry. SU2, the 3 sphere, so pi 3 is Z. And we saw on Monday that this is also Z. So I get a homomorphism from Z to Z. Must be multiplication by some integer. And the question, what's the integer? So for this group, I claim it's an isomorphism. But if we look at the other inclusion, so again I get a map from pi 3, which is Z, into pi 3, which is Z. And this I claim is multiplication by 3 instead of 1. So it's not an isomorphism. So they're really very different subgroups. They have different topology if you want to. For example, implies that if I take a G2 mod SU2 and G2 mod SU prime 2, they have different homotopy type. Right? Look at the long homotopy sequence. This is one part of the homotopy sequence. This tells you that in the next step I get pi 3 of the quotient. So it probably implies that here pi 3 is Z3, I think, and here pi 3 is 0. Like this is the one that occurs over there, which is a unitangent bundle of S6, which certainly has pi 3 equal to 0. But this is a very different manifold. Same dimension, right? Same groups. It's a homogeneous space with the same groups, but the homotopy groups are different. Okay, very peculiar fact. So let me just mention maybe as something, a future comment. In general, if I have, say, G, a simple Lie group, simple compact Lie group, and H, a simple compact subgroup, Lie subgroup, then I get the inclusion from H to G. And one of the facts about compact simple Lie groups is that pi 3 is equal to Z. So I get an induced homomorphism from Z to Z for every simple subgroup of a simple Lie group. And that must be multiplication by some integer. Right? So to this situation is associated an integer in Z. And that's called the Dynkin index. Of H and G. Implication is that, for example, pi 1 of G mod H is Zn. So it has a topological implication for the quotient. Okay. That's all I want to say about G2. There's some other funny facts about G2, which, from what we know so far, is not so easy to prove. Pardon? Oh, pi 3, I'm sorry. Pi 3. Just like in the situation over there. Yeah, pi 3. G2 lies in SO7. And I claim SO7 mod G2, so that's a homogeneous space. What is it? I claim it's RP7. That's, from what we know, a little bit hard to see. And if I look at the two-fold cover of SO7, which is spin 7, this is a sphere. So it's another funny way of writing a sphere as a homogeneous space. Okay. And often in applications, it's very important to understand in how many ways can I write a sphere as a homogeneous space, besides the standard one that you know. And they're classified, and this one and the one for S6, I've done earlier some of the exception ones. And there's only one more exception one. That's spin 9 mod spin 7 is S15. So these three using exceptional Lie groups, then everything else is a standard one for classical Lie groups that we saw before. That's a non-trivial theorem. Very important applications. Okay, that's it. And let's go back to Lie algebra, general Lie algebra theory. That's a pretty picture, I like that. Also very useful in geometric applications. In fact, that kind of question is often an interesting question, an important question. If I give you, say, the Lie group SON, what are all the subgroups of SON? Describe them all up to conjugacy. That's, in general, not so easy. The methods that one uses to do this, representation theory. Right, if I have a subgroup in here, there's X on Rn. That means that Hx on Rn, and that's the representation of some compact Lie group. So I have to understand the classification of the representations of compact Lie groups on Rn up to conjugacy. And that's a non-trivial problem, which we'll discuss the next section. For small n, this is doable. For large n, it's not so easy. Okay, so our next topic is nilpotent and solvable Lie groups, and Lie algebras. Here I write down the main results. I'm not going to prove very much except for one or two things, and more proofs in the notes that we have to get somewhere. So first, if I take Lie algebra G, I can define two series. So this is a usual thing that you know for groups also, right? G upper K, so G upper K is defined as the commutators between G and Gk minus 1 inductively, where G0 is G. Then I have a corresponding lower one where I take the D brackets between Gk minus 1 and Gk minus 1 as opposed to all of G, so it sits inside here. And then again G0 is G. So these are two series associated to every Lie algebra. And then I say that G is nilpotent. So K-step nilpotent if Gk is equal to 0, but the previous one is not. And it's solvable. And then K-step, similarly, for the other series. And for Lie group, I just define Lie algebra. So G is nilpotent, solvable, if and only if G is. I could look at the commutators of G, but that turns out to be not a good idea. And the last one could be a finite group, if I do this. And that finite group, when I take commutators, might never be 0. So it might not be solvable in the group sense that you're used to, but the whole theory of such Lie algebras is usually the same thing as when the Lie algebra is solvable and nilpotent. So that one should do it on the Lie algebra, not on the Lie group level. Examples that we saw, certainly we saw one already. Generalized Heisenberg group as nilpotent. two-step. And most important examples is the upper triangle matrices. This is solver. So meaning here I allow any entry, say over the reals, over the complex numbers, doesn't matter. Right? So it's a real solver Lie algebra or a complex solver Lie algebra, but everything below the diagonal is 0. And if I do it so everything along the diagonal is 0, this is nilpotent. And all one needs to check is that when I take commutators, what happens. That's maybe an exercise. That G so let's look at example 3. And G, we call it upper K, I guess, is a matrices where this is 0, but the rest is not. So zeros move up when you take commutators. Okay. So of course then it stops after as many times as the size of the matrix. And example 2, I just observe that if I take the commutator once, then I get zeros on the diagonal. Right, because if I take commutators, it's AB minus BA along the diagonal, so that's going to be 0 since it's commutative. So the commutator lies in here, because then by this remark it ends up in 0. So even stronger, the commutator is nilpotent. Right? So, and the basic theorems are, or maybe the most basic theorem is that is the following. If G is nilpotent, then there exists an N such that G is contained in, what should we call that, example 3, upper of size N. So every nilpotent Lie algebra is a subalgebra of one of these. So it's the daddy of all nilpotent Lie algebras. I just have to make the size large enough depending on which one I start out with. Right. And similar for the solver ones. So then exists the answer that G is contained in example 2 for size N matrices. You might think, well, now I know all nilpotent solver Lie algebras. Right? They're all separate of this one. I know this one. Well, that's misleading. That's far from true. If I want to classify such Lie algebras up to isomorphism, say, that's unsolvable for general N. Even for small n, that's a lot of work. Say small n being the size of the matrix is small, right? For small n, you can do that, but it gets very, very complicated very, very quickly. So just because the subalgebra of this is not the whole story. But nevertheless, this tells you a lot about such Lie algebras. Properties. First about this lower and upper series are defined over there. Gk and G lower k are ideals in G. G nilpotent k step implies that the last one, Gk minus 1, is an abelian adder. Sorry, even more than that, right? So the last one if gk minus 1 is non-zero, it commutes everything. So it lies in the center. So the last one is in the center of G. And if G is solvable, again k step, then the last one, G is upper or lower k? I always forget. Lower k, right? G lower k minus 1 is an abelian ideal. So certainly what this here says is the last one commutes, it's abelian, right? That's what this is here. And they're all ideals, so this is an abelian ideal. So every nilpotent Lie algebra has a center, and every solvable one has an abelian ideal. Okay. Important basic properties. Other important properties. Subalgebra of a nilpotent or solvable Lie algebra is nilpotent or solvable. If you accept this theorem, it's obvious, right? And it's a subalgebra of the upper triangular matrices, so certainly, but these are not so easy to prove, so whereas this one is not so hard to prove directly. Other important properties. If A is solvable, then A mod B for any ideal B is solvable, respective to nilpotent again. So quotient Lie algebras, which I can form if this is an ideal in here, so there's a quotient Lie algebra. So that descends, this property descends to a quotient. And another important property is that if I have a long exact sequence, then if the ends A and C are solvable, then is the middle. But this is not true for nilpotent Lie algebras, this last property. So here's one difference between nilpotent and solvable. Maybe just one quick example of E is false for nilpotent ones. I give an example in the notes, but the example is wrong. An example would be the Heisenberg group. Sorry. No. What am I saying? Oh no, sorry, the example is right. There's one claim in there which is wrong, but the example is right. So what's the example? I take a three-dimensional Lie algebra spanned by x, y, and z, and the only non-vanishing Lie bracket is that x, y is equal to y. Everything else is 0. That's a Lie algebra. Notice that if I keep taking brackets with everything, I keep getting y. Bracket of this with y, with x again, gives me another y. So this is not nilpotent. But it's solvable. Right? The first commutator is y, and the next commutator is 0. So 2 steps solvable. And now I can just say the following. Take the exact sequence r times x goes to g, goes to the span of y and z, which is simply R2, and y and z commute, so it's a trivial algebra. And this, of course, is trivial algebra. So this and this is abelian, therefore nilpotent, but this is solvable. So this shows that this fact is not true for nilpotent ones. This and this one is not necessarily. It's solvable, but not necessarily nilpotent. So that's an important difference. I'm not going to prove these theorems on the blackboard. The notes contain certain indication how these are all proved. It's essentially just a Jacobi identity all over again. So you should read it on your own. These are more difficult. One thing one has to use is Ado's theorem that every Lie algebra is embedded in a matrix Lie algebra. But you also prove the following theorem, which is useful. If I have a subalgebra of the matrix algebra of matrices, right, such that if A is an element of G, so that means A is a matrix, then it's nilpotent. So if every matrix inside G is nilpotent, this implies G is nilpotent. So that's non-trivial, right? I give a proof for that in the notes. That's an important fact. Corollary. If I have a Lie algebra G such that ad x is nilpotent, then G is nilpotent. So I regard ad x as a matrix and use this theorem right here. Other way around is certainly also true. Right? If I have a nilpotent Lie algebra, what does ad x do? It takes G, what was that, upper K, into G upper K minus K plus 1. Right? This was Lie brackets of anything with GK. So ad x moves it down. So it moves it down and down and down, goes to 0. That means the trace, that means ad x as a matrix is nilpotent. So one direction is obvious, the other one is non-trivial, and that's a corollary of this result right here. So this is a very useful fact. Excuse me. One more fact is a theorem that G is solvable if and only if the commutator is nilpotent. So one direction is obvious, I claim, right? If it's, I guess, this direction, that's clear. If the commutator is nilpotent, then further commutators of gk minus 1 with gk lie in g comma gk, which is what makes this nilpotent. Right? So it sounds even stronger, right? To say this nilpotent sounds much stronger than saying G is solvable, but it's not. One way to make it plausible is to use a theorem that I just erased, that every solvable Lie algebra is a subalgebra of the upper triangular ones. Because the commutator of that is everything 0 on the diagonal. That's nilpotent. So if G sits inside here, the commutator sits inside the general nilpotent one. So that makes it plausible if you assume that theorem. Of course, you use that to prove the theorem. So quite honest. One more theorem. So is that an if and only if? I think so. Oh, yes. G is solvable. So another strange characterization of solvable. If and only if the killing form G vanishes on G comma G. That's a strange result. Let me just make a few comments. Notice that when G is nilpotent, that implies the killing form is 0. That's because ADX was nilpotent. And B of x comma x was trace of ADX squared. So ADX squared is nilpotent, the trace of a nilpotent matrix is 0. Right? So certainly for a nilpotent Lie algebra, the killing form is dead 0. So one direction follows from here, right? If it's solvable, this one is nilpotent, which means the killing form vanishes on here. Furthermore, this is an ideal inside G. So in fact, the killing form of G restricted to this algebra is just the ideal of this algebra. Well, the exercise. So again, one direction follows easy from this. What's surprising is the other direction, right? It sounds even stronger than this theorem here. It says that if the killing form of this on this ideal is 0, it certainly is a consequence of being nilpotent. That sounds much weaker than being nilpotent. So if this is true, then the Lie algebra is solvable. It's even stronger than this one. So that's interesting. I proved this one in the notes, but not this one. So corollary, for example, if G is a Lie algebra such that the killing form is 0, this implies G is solvable. But not necessarily nilpotent. Well, the killing form is dead 0 on the Lie algebra G. It's 0 on the commutator, because that's an ideal. If it's 0 on the commutator, this theorem says it's solvable. Okay. So that's how it's a corollary of this theorem. And one can give examples. I think I'm asking for that in the exercises. Give an example of a Lie algebra which is solvable but not nilpotent, whose killing form is 0. But I don't think they're classified. It's an interesting question. What do all the Lie algebras look like whose killing form vanishes? That's an interesting question. I'm not sure what else one can say in addition to this property. I'm sure there are other things one can say, but I haven't checked. Since the killing form is such a basic invariant of a Lie algebra, it's kind of an interesting question. When does it vanish? Okay. So let me start the important topic that I want to get to in more detail. About semi-simple Lie algebras. She is called semi-simple. And there are various characterizations. One is if G has no abelian ideal. And G is called simple. if G has no ideals. Because besides the trivial ones, 0 and G, of course, are ideals. If there's no other ideals whatsoever, it's called simple. And convention is that I don't want to consider the one-dimensional Lie algebra, which of course has no ideals. Right? I don't call that simple. There are various reasons why that's not a good idea. So certainly simple implies semi-simple, right? But certainly not the other way around. So we're going to study and classify these semi-simple Lie algebras, both over the complexes and over the reals. Over the reals is much more difficult than over the complexes. So we'll do it first with the complex numbers, and then look at what we call real forms to classify the ones over the real numbers. First, say to put this into a more general context, let me just mention another important concept called the radical. Which is the following. So first notice that if A and B are solvable ideals in G, then so is the sum. Meaning this pair, there might be intersection. I'll just take the sum of these as vector spaces, and certainly a sum of two ideals is a certain ideal, but if these two are both solvable, this is also solvable. You can get this as from a consequence, probably from this exact sequence that we discussed down here. This implies, so hence, there exists a maximal solvable ideal for the radical. Since the sum of any ideals is an ideal again, it's solvable, therefore there must be a maximal one. G is finite dimensional. So that's called the radical. And so another equivalent definition of G being semi-simple. That's if and only if the radical of G is 0. So if and only if there are no solvable ideals. So here I said there are no abelian ideals. It's actually, I could just say there are no solvable ideals. It's the same thing. Because remember, if I have something solvable, the last step in the descending series was an abelian ideal. Right, so, okay. Then there's another theorem that's very useful. That take G any Lie algebra, take the radical inside G, and the claim is there exists a subalgebra H inside G, which is semi-simple in the above sense and unique up to automorphism. Such that the Lie algebra G is the sum of the radical plus H, and the intersection is trivial. So it's a direct sum of something that's solvable and something that's semi-simple. H is not an ideal, so this is not a sum of ideals that you can expect. That's an ideal, that's a subalgebra. This one is solvable, this one is semi-simple. So for example, from this one, it's not hard to see that this implies that G, not the radical of G, since that's an ideal, that's a Lie algebra, is same or something. Okay. That's not so hard to see. This one is a not such a, is a difficult theorem. I think it's due to Malchev, maybe, I forget who's that associated to. One of the useful applications of this kind of theorem is that one can do some kind of induction, right? If you want to prove something about a Lie algebra, it's often sufficient to prove it for a semi-simple Lie algebra and for a solvable Lie algebra. Then use a theorem to try to prove that's that property for the whole for any Lie algebra also. So for example, one thing one proves using that is a following theorem. Say G is a connected Lie group. This implies there exists a compact subgroup connected K and G, unique up to automorphism. Such that G is diffeomorphic to K cross some Euclidean space in a certain dimension. Was not isomorphic, but diffeomorphic. So it says the topology of every Lie group is the same as the topology of a compact subgroup. So this is called the maximal compact subgroup. And it's unique up to conjugacy. There's a unique subgroup up to conjugacy, which is compact and which is maximal.
It corresponds to the Cartesian to the algebra?
No. So for topology of Lie group, it's sufficient to understand topology of compact Lie groups as a particular consequence. But this fact is certainly also very useful. And this is one of the steps in the proof using this kind of radical decomposition. Maybe one more result before I start more seriously with semi-simple Lie algebras is following theorem. If G is nilpotent, so as a Lie group, remember, it just means the same thing as saying the Lie algebra is nilpotent and connected. Then the exponential map from the Lie algebra into the from the Lie group, from the Lie algebra into the Lie group, is a covering. So particularly if it's simply connected, this implies X with a diffeomorphism. And it's onto, certainly also. It's always onto. It's part of being a covering. Remember, you saw examples where this exponential map is not onto. For nilpotent one, it always is onto. Another related property is that if I have a subgroup inside the general linear group, which is nilpotent, then X was a diffeomorphism. So for matrix Lie groups which are nilpotent, it's always a diffeomorphism. For general Lie groups, it's at least a covering. And one proves, in order to prove this, one proves this first here. This is not so hard. One uses that to prove this.
If I have a Lie algebra and then a Lie subalgebra and it's solvable, Is it an ideal?
No. So I even have abelian subalgebras, so which are certainly solvable, which aren't. I can have abelian subalgebras which aren't ideals. For example, maximal tori that we discussed later on, or any torus inside SON, for example, right? Or inside UN, like diagonal matrices, for example. That's solvable, but in general they're not ideals. Like this Lie Lie group is simple, there are no ideals whatsoever. So abelian ones aren't ideals. So the answer is no. To say something is solvable ideal is much stronger than saying it's solvable subalgebra. It's much, much stronger. So in the radical, I had to assume, look at the maximum solvable ideal. Right? So that additional word is very important. So one quick application. Example, let's assume G is nilpotent. Remember, this implies that the center of the Lie algebra is non-trivial, because the Lie algebra is nilpotent. This implies that the center of G is not finite. It's not abelian. So that means that, for example, the identity component is equal to some abelian group. Could be a quotient, actually has to be RK, but that's not so important. And now remember, I can take any lattice inside the center. Then this implies that G mod the lattice is also a nilpotent Lie group. But it's a Lie group, we discussed that before. Certainly has the same Lie algebra because cos gamma is discrete. Lie algebra is nilpotent, that's another nilpotent Lie group. But of course, part one of this Lie group is non-zero. G is simply connected, then it's equal to gamma. So that means such a G mod gamma cannot be a matrix Lie group. Because of part B. B says that if I have a matrix Lie group, X is a diffeomorphism, which means G must be simply connected. Because the Lie algebra is simply connected. And of course, for such example, that's not the case. So there are many, many nilpotent Lie groups which are not matrix Lie groups. Although every nilpotent Lie algebra is a matrix Lie algebra. Okay, so that's enough on nilpotent solver. There's a lot more things one can say, but I don't want to get lost in that subject. It's a very different subject. I want to start more thoroughly with solver ones next week. Friday is supposed to be an exercise session. So I printed out remaining exercises from the notes in the first 2 pages, and the last 2 pages are the ones from the previous one. And I think, let's see, the first one should be a sign-up sheet. Do you have that? Okay. So problem sessions on Friday. We certainly can't cover all problems, that's clear. 1 to 2:30. You guys picked out a room for that. It wasn't this room, I think, right? Does someone remember what room it was? Pardon? 349. So sign up for a problem. At least maybe everyone can sign up for at least one problem. So everyone go on the blackboard. In these exercises, I circled about 8 or 9 of them, which I think would be useful to do, just to have a selection. We can't do all of them. And if there are any problems from the last assignment that haven't been discussed yet, we could also do those. Right? So take a look at what you want to do and then present something on Friday. Okay? And he has a sign-up sheet, so he's going to try to make everyone sign up for something.